Today on Macaulay Math, we're talking area and sigma notation. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, Lesson 22 on area and sigma notation. Our goals for today. We're going to use sigma notation to write and evaluate a sum. We're going to understand the concept of area. We're going to approximate the area of a plane region, and we're going to find the area of a plane using limits.
Just as the foundational use of the derivative is to calculate slopes of tangent lines, the foundational use of the integral is to find the area under the curve. The definition of the definite integral uses the limit of an infinite sum of rectangles. To prepare for that, this lesson reviews sigma notation. Sigma notation is used to concisely write and evaluate series. If we use sigma notation to approximate the area under a curve by using it to calculate the area of a number of rectangles that will fit under that curve, we will also discuss the error that this method creates and how that error can be minimized to produce better approximations. Okay, quick review of the use of the integral. The foundational use of the derivative is to find the slope of a tangent line at a point. The foundational use of the integral is to find the area of a curve over a closed interval a to b. An area of an irregular region can be approximated by finding the sum of regular parts. Let's take a look at a quick demonstration. Suppose we have a function given here in yellow. On a given interval from a to b, the area under the curve means the area between the curve and the x-axis shown here in blue. If we divide the interval into 4 equal subintervals and sum up the areas of the 4 green rectangles calculated by using left endpoints of each rectangle shown here, we will have an approximation of the area under the curve. In this case, it is an under approximation of the actual area under the curve. If we use right endpoints of the subintervals to calculate the area of 4 rectangles shown here in red, the approximation will be an over approximation of the actual area. Additionally, if we increase the number of rectangles and reduce the width of each subinterval shown here in purple, the approximation will become better, but the amount of work needed to calculate the approximation increases. A quick review of sigma notation. Sigma notation is an easy way for us to reduce a long series into a small, compact notation. This sigma notation has an index of summation. This I here is the value that is being counted. So it's the value, it's the variable of the sigma notation. A sub I is the ith term of the sum. So whatever term you are currently on, that is your A sub I. 1 in this case is our lower bound, n in this case is our upper bound. In the case of the summation, n is not a variable, it is a constant. The only variable in the case of the summation is the I. Example, write the following series in summation or sigma notation. So I look at this expression here and I want to write it in sigma notation. So when I'm finished, I need some sort of sigma, and I'm going to start with I equaling 1, and the first thing I need to do is I need to figure out how many terms are in this notation. And so I start looking. I have 5s on the top, and they're all 5s. I have 2, 3, 4, 5, up to 21. So it looks like they're counting here. So this looks like a arithmetic sequence that goes from 2 to 21. So arithmetic sequence can be represented by a linear equation. And so what I can do is I can say that this is my first term and this is my second term. I can say that this has the point 1, 2 and that this thing has the point 2, 3. And we can make an equation, a linear equation. And so real quickly, I can say that my slope of this thing is 3 minus 2 over 2 minus 1, which is just 1. And then I can use the point slope formula and go y minus 2 equals 1 times x minus 1 and say that my final equation is just going to be x plus 1. And so if I want to know how many terms are in this thing, I can go 21 equals x plus 1 and say that x is just equal to 20. Now 20 is going to be my upper limit of summation. So the next thing I need to do is I need to figure out what kind of an equation I'm going to put here. Since we have a fraction, might as well make it a fraction in our equation and make an equation for both the numerator and the denominator. Now the numerator doesn't change. It's a constant, so I'm just going to make it a constant. The denominator changes, and we've already come up with an equation for that denominator changing. Now I can't use x because my index of summation is I am just going to change that to I plus 1, and we'll put a box around that, and we'll be done. Summation formulas. Here are some formulas that will allow you to find the sum of certain simple summation equations. As a for instance, if you want to add up n terms that are just I, the counting numbers, 1, 2, 3, 4, 5, you can use this equation here. If you want to sum up the first n terms of the first counting numbers squared, you can use this equation. Let's look at an example. Use the summation formulas to find the following sum. So I look at this expression here, and I see I squared, I see I see a constant. All of those things are part of these summation formulas. So I can easily break this thing down and add those values up. Here, I will rewrite this . And so I'm going to go to the sum as I goes from 1 to 50 of I squared minus 3, the sum as I goes from 1 to 50 of just I, plus the sum as I goes from 1 to 50 of just 5. And now I can replace that first sum with this equation here, the second sum with this equation here, and instead of putting in the n values, I'm going to substitute with the given value of 50. So let's do that. So I'll have 2 times, and again, the I squared equation is going to be, in this case, 50 times 50 plus 1 times 2 times 50 plus 1 all over 6. So let's write that. 50 times 50 plus 1 times 2 times 50 plus 1 all over 6. And then it will be minus 3 times 50 times 50 plus 1 all over 2. And then the constant, you go back here, if you have a constant, it's just the constant times the number of terms. So we'll have plus 5 times 50. And if you do it all in a calculator, you'll see that you'll have 2 times 42,925 minus 3 times 1,275 plus 250, and that will give you a total sum of 82,329. Example, using left and right endpoints and the given number of rectangles to find 2 approximations of the area under the curve. Alright, so I have this linear equation, and they want me to go from 2 to 6, and they want me to use 6 rectangles. Alright. I also need to do left and right endpoints. That seems like a lot of work at first. But let's see if we can't try and make it just a little bit easier for us. So first, f of x equals 9 minus x. Well, let's draw that real quick. This is a linear equation that has a slope of -1 and a y-intercept at 9. So if I go, this is my y-axis, this is my x-axis, I put a 9 here. I put a 9 here. There is my linear equation, but they only want us to go from 2 to, let's say, 6. Now, I'm not sure that that's going to be perfect, but I need 6 rectangles. Okay, 6 rectangles. Well, the difference from here to here is 4, so it's not going to divide nice and easy. So let's see here. If I divide it in half, and then I divide these into thirds, now I have my 6 rectangles. I got to figure out how far each of these are. So our delta x in this particular instance, our change in x in each one of these is going to be delta x. That's going to be 6 minus 2, the difference here, divided by the number of rectangles, 6. All right, so our width is going to be 2/3. So each of these is going to be 2/3 long. All right, so if I want to figure that out, let's see here. My endpoints, my axis for these endpoints are going to be 2 as 2/3 is going to be 6/3. So 6/3 plus 2/3 will be 8/3. 8/3 plus 2/3 will be 10/3. 10/3 plus 2 will be 12/3, but that's 4. 12/3 plus 2 will be 14/3. 14/3 plus 2/3 will be 16/3. And then 16/3 plus 2/3 is 8/3, and 8/3 is 6. And that makes me happy because we know that our endpoint is supposed to be 6. Now, if I wanted to draw in left endpoint rectangles, those left endpoint rectangles will look something similar to this. Now, here's the thing. My right endpoint rectangles will look something like this. If I start here and go down, and then I'll have to start here and go down, and then I'll start here and go down, and then I'll start here and then I'll go down, and then I'll start here and then go down, and start here and go down. You'll notice this rectangle and this rectangle are the same. This rectangle and this rectangle are the same, and we have some matches here. So let's simplify our work by making a table. Move this table. All right, call this our x. Let's call this f of x. Let's call this delta x. And let's call this the area. All right, so our x's. If I go 2, I go 8/3. I go 10/3. I go 4. I go 14/3. I go 16/3. And I go 6. Now, here's what I'm going to do. I'm not going to show it. I have it off to the side here on a calculator. But you can plug this into the calculator and you can calculate these heights by plugging 2 into this function. So I'm not going to do all of them by hand. I'm just going to give them to you just to keep the time safe. But just for 2, and we'll do the whole number one. So if I go 9 minus 2 will be 7. If I go 9 minus 4, I'll get 5. And if I go 9 minus 6, I'll have 3. All right, so those are easy to calculate. The remaining ones are 19/3, 17/3, 13/3, and then 11/3. Now, if I want to find the area of each of these rectangles, I need to multiply these calculated heights by the change in x. Now, luckily, our change in x is the same for all of them. We've already calculated that. That's going to be 2/3, 2/3, and if we multiply 7 times 2/3, we will find the area of this first red triangle. It has a height of 7 and a width of 2/3. If we do that multiplication, I'm going to get 42 ninths. Now the reason I did it as ninths is because when you come down here to this next one, you'll have 19 thirds times 2/3, and the 19 times 2, well, that's not too bad. That's just 38, but 3 times 3 gives you ninths. So eventually I'm going to have to add these up. So I wanted a common denominator, so I changed it. All right, so I'm going to do all the rest of these multiplications. So I get 34 ninths, and you might see a pattern happening. Each time it goes down by 4 ninths, which is 2/3. And so I'll have 30 ninths, I'll have 26 ninths, I'll have 22 ninths, and I have 18 ninths. Now the reason I did all this work is because if we do left endpoints, it'll be these first top 6 triangles as the sum. And we do this because we have, again, some repeated rectangles. This green rectangle is the same as this red rectangle. It's just a different side. So if we do our left endpoints, we're just adding up these values here. So if I want to do my left endpoints, I'll be adding up these first 6, so I'll just put them down. It'll be 42 over 9 plus 38 over 9 plus 34 over 9 plus 30 over 9 plus 26 over 9 plus 22 over 9. And that ends up equaling 92 over 9 units squared. And then if I want to do the right endpoints, again, I'm starting here, so it'll be 38 over 9 plus 34 over 9 plus 30 over 9 plus 26 over 9 plus 22 over 9 plus 18 over 9, and that ends up equaling 168 over 9 units squared. Now, the red rectangles are going to be an over approximation, and the green rectangles will be an under approximation. Boxes around those. All right. Next example. Find the limit of s sub n as n goes to infinity. All right. So here's what we're trying to do. We're trying to find the limit as n goes to infinity of s of n. Now in this case, that limit as n goes to infinity is 81 over n to the third times the quantity n times n plus 1 times 2n plus 1 all over 6. Now we could spend a bunch of time multiplying all of this out, and that would be perfectly okay, but we're trying to make this as short and as easy as possible. And we know that when we do an infinite limit and we have a rational function like this thing is clearly going to be, we know that the only thing that matters is the leading coefficients. So at some point, I will be multiplying 81 times n times 2n. Now when I do that, I am going to get, so n times 2n will be 2n to the third times 81 will be 162 n to the third, and then it will be plus some other terms. And again, you could spend the time to calculate all of that, but it isn't going to matter in the context of this problem because we're doing a limit at infinity. We only care about the degrees of the numerator and the denominator. That's it. And on the bottom, n to the third times 6 will be 6n to the third. Now, because our leading terms are of the same degree, we can find the limit of that by comparing the leading coefficients. And so these terms here, they didn't make a big difference in the context of this problem. This limit is just going to be 162 over 6. And that turns out to be, if you put it in your calculator, you get 27. All right, final example. Find the formula for the sum of n terms and then use the formula to find the limit as n goes to infinity. So here we're going to have a similar situation as the example in the last problem. We are going to use these summation formulas to change this limit into an expression that we can calculate very easily. So we look at this. I have two variables. I have this n as n goes to infinity, and I have this summation with an index of I. In the context of this summation, n is constant. It is the upper limit of summation. And so in the context of this particular issue, n is a constant and can be moved out front. With the rest of the constants. And so I can rewrite this as the limit as n goes to infinity of, well, 2 times 2 is 4, and n times n is n squared. And then that all that is left inside the summation is I equals 1 to n of just I. So 2 times 2 will bring the 4 out. That's a constant. N times n. I bring that out front and get n squared. In the context of this summation, n is a constant and the 4 is a constant. So now I'm going to replace with a summation formula. And if you look back here, the I formula is replaced with n times n plus 1 all over 2. So equals the limit as n goes to infinity of 4 over n squared times n plus 1 all over 2. And so now we're in a situation like the last example. Find the degrees of the numerator / denominator. So let's do that. All right, so at some point, if I multiply this whole thing out, I'll have 4 times n, which will give me 4n squared plus some other terms. In the denominator, I'll have n squared times 2. That'll give me 2n squared. So here I'm going to find the limit at infinity. And because the degrees of the numerator and the degree of the denominator are equal, the way that we find that limit is just to again compare the leading coefficients. So that limit will be 4 over 2, which will just be 2. All right, well, that's all I got for today, folks. So the Star Wars fun fact of the day. In Empire Strikes Back, Darth Vader tries to get a bunch of bounty hunters to find Han Solo, Princess Leia, Chewbacca, and the Millennium Falcon. These bounty hunters in canon all have names and backstories. And their names are, this guy is Dengar, this is IG-88, this is the famous Boba Fett, the most famous one of all of these bounty hunters. This one is Bossk, here is Forlom, and this last one is Zuckuss. Well, that's all I got for today, folks. Have a good day. Bye.